Today, we're going to New York using Google Maps. How does Google Maps find the best route? So it all starts with data. The data in this case is the cities that I can travel from Toronto to get to my destination. I can go through Pittsburgh, Cleveland, go to Trenton, New Jersey, New York. I can go through Kingston, Albany, New York, go through Buffalo, Scranton, New York. When I set up my data like this, what I have is what's called a graph. It's a directed or non-directed graph. It's a set of nodes which are connected by segments, and the segments have a certain weight, length, distance, a number, a real number, which is a function of two nodes. Some of these nodes are connected, like Toronto and Kingston, and others are not directly connected, like Toronto and Pittsburgh. From this perspective, the problem of finding the best route is a problem in combinatorial optimization or graph optimization. There's different elements that go into this. And today we're going to describe what those methods are. We're going to describe the method which was the original one, done in 1959 by the Dutch mathematician Dijkstra. There are better ones now. In fact, a lot of the machine learning tools have been devoted to enhancing algorithms such as this one, but this one is still solvable within the context developed more than 50 years ago. In other parts of this course, we'll discuss enhancements to this based on machine learning, heuristic methods, and artificial intelligence. Given a graph that summarizes all the possible routes and all the possible distances, and the distances could be done with any metric. It could be adjusted for velocity, speed, difficulties. The graph will have connecting lines with a certain weight attached to them. The weight could represent the distance between nodes or the time it will take to get from one node to the other, a number. This is what we will depict as the length of the graph between nodes. The graph is going to have n possible nodes, which represents all the possible cities we could travel through, and this could be millions. And we're going to have a starting node, which we will denote by 1 in our sequence, and the target node, which we'll denote as capital N in our target sequence. Our objective is then to find the shortest distance between node 1 and node N. We do this by creating an iterative method. An iterative method which is going to have as a key our ability to keep certain information from one step to the next. The key to the Dijkstra algorithm to work is that we organize the information efficiently. We only remember, we have a certain memory that allows us to remember the information that matters. We will quickly forget information which is not relevant to carry out our step. And all of this can be codified into the following objects we're going to be creating interactively. We're going to have a set of nodes, which will be our finalized nodes. These are the nodes that we already know what the optimal distance will be how to get there and what the total distance is, and a set of non-finalized nodes. These are the ones that we still do not know what the best path may be. We may have a solution, we may not have a solution. We don't know what that optimal solution is going to be. And then we're going to keep also a list of temporary lengths that are going to be our benchmark to improve upon every time we run a new iteration on the graph. One interesting remark is that not only we will find the shortest distance between the origin and the end, in the process we're going to find the shortest distance between the origin and all of our nodes in the entire map, all of them at the same time. The distance between the beginning and the end will just be a particular case of all the optimal distances we will find between the beginning and anywhere else in the nodes of our graph. So once again, we're going to have a set that we'll call L, which will contain nodes whose shortest paths from the start node is finalized. At the beginning, that will be the empty set. We don't know anything, any node. We approach the problem without any knowledge as to what is optimal. Everything is possible. This list, L, is what will allow us to monitor progress as we go ahead in our iteration. Next to that, we're going to have a set N, which stores the nodes whose shortest path from the start node is not yet finalized. At the beginning, that will be the entire graph. Again, we approach the graph without any knowledge of what is best. So if the set N measures our degree of ignorance, the set L measures our set of information which is definitive. We know for sure that for certain nodes the shortest distance is a certain number. At the beginning, our ignorance is the full graph, and our knowledge is the empty set. As we go ahead in this iteration process, we're going to store a list that contains the shortest path, which are temporary only for that step. The shortest temporary path from the start node to each of the nodes in the entire graph. At the beginning, it will look something like this. The node where we start, we know the shortest distance is 0. If we live from Toronto, the distance from Toronto to Toronto will be 0. Every other city, we will assume that the distance is infinity. Niagara Falls, infinity. New York, infinity. Philadelphia, infinity. Only Toronto is going to have a distance of 0. Mississauga, just outside Toronto, infinity. This is our temporary shortest length from our start node to each of the nodes in the path. We're also going to remember for all of the nodes in our graph denoted by J, the label J, we're going to keep track of labels K sub J, that for each node J tells us the previous node we traveled before reaching node J using the shortest path. So we're going to have a type of memory that tells us for our optimization solution the previous node that took us here. Just the previous node, not the 2 or the 3rd previous node, just the previous node that took us here. With all of this information organized in this way, we can now set up the recursive algorithm that is guaranteed to converge to the optimal solution of our optimal distance path from node 1 to node n. We start like this. We're going to have an iteration. This is going to be the iteration 0 in our graph process. And as we mentioned, the amount of ignorance we have is for all of the nodes. Note, we even include node 1, which is Toronto. We claim that we don't even know what is the fastest way to go from Toronto to Toronto. Because of that, the amount of knowledge we have is the empty set. Now, we do know that the shortest distance from all of the nodes in our graph to Toronto is going to be Toronto, 0. The other cities, infinity. This is how we set it up at the beginning. And this is the resulting graph with all of the information there. Toronto, or node 1, distance 0 to itself, and we grow this iteration process through next door neighbors. Next door neighbor to Toronto, node 1, is node 2, 3, and 4, because these are the nodes we can move to directly from node 1. And we can see that of all of these nodes, the optimal distance from Toronto is, for node 2, distance is 2. For node 3, distance is 8. And for node 4, distance is 7. So we'll record that in our next iteration process. Here it is. These are the optimal, temporary optimal recorded distances from Toronto. Again, Toronto is 0. Node 2 was 2. Node 3 was 8. And node 4 was 7. All others are infinity. We record that in our vector D1, because now we're doing the first iteration of our recursive method. We also conclude that node 1, which is Toronto, has an optimal distance to itself. The optimal distance is 0, it's here. Therefore, our set that represents our knowledge, set L, contains the city of Toronto, which is removed from the set of ignorance nodes. Toronto is no longer there. We know that the optimal distance from Toronto to itself is 0. This is trivial, but this is how we get this algorithm on its way. And for our memory list, the one that tells us where we were prior to getting to that node from the city of origin, what we have is Toronto, which is an obvious solution because we're not going anywhere, is recorded as 0. Also, we record as 0 the nodes that we have not yet reached, and the nodes that we have reached, we record them as what they are, which is node 1. We were in Toronto, node 1, before we got to each of those 3 nodes. We have gained something in this iteration, and that is the knowledge that to go from Toronto to Toronto, the distance is 0, and we don't have to leave the city. But this is how it starts. This is clearly obvious. That is the price we pay. It's an obvious first step. But this algorithm, this method of optimizing the distance in an iterative process has now started and will allow us to move on until we obtain a set L, which is all of the graph, and a set N, which is the empty set. In the next iteration, we observe that of all the optimal distances from Toronto, node 2 gives us the shortest distance to Toronto. So we take that as our first destination, and now we examine the next door neighbors of node 2, which happen to be node 3, node 4, and node 5. Node 6 is not a next door neighbor, so we don't get to it yet. And now what we do is we perform a similar analysis, taking node 2 as our starting node. We know that from Toronto we're going to move to node 2. And from node 2 we examine the possibilities that we have with its next door neighbors, being nodes 3, 4, and 5. In doing that, we now calculate an updated optimal distance to Toronto, to node 0 from each of the nodes, which are next door neighbors to node 2. The result is what we have here. Node 1, node 2, and then the rest of the nodes. The distance, for example, to node 3, which looks like 8, we now see that it's actually 6 if we go from node 1 to 2 and then to 3. This is clearly indicated here. You see, for example, that in the previous iteration, the number 8 was our previous optimal number. This optimal number is now replaced by a better one because we now know that we're going to go from Toronto to node 2. Therefore, the distance that used to be 8 is now replaced by a smaller one. This is part of our iteration process because we have now replaced the city of Toronto, node 1, by node 2. And every analysis we did before is now going to be done starting from node 2. Note that the distance from node 1 to node 4, the optimal distance continues to be 7. This is reflected on our memory list. Node 1 continues to have a 0 in it because it's a trivial solution. Node 2 has 1 because we're going from the city of node 1 to node 2. Note that node 3, the optimal solution reflected there is the one that comes in this direction. So the node prior to this one is now node 2. Node 4 that we have here tells us that at this stage, the optimal distance continues to be the one that comes directly from node 1. We don't know if we can do better. There may be a way to do better, but at this point in time, in this iteration, the optimal distance from node 1 to node 4 continues to be the direct one, and that's reflected here and here. For node 5, what we see is that what we note is that the optimal distance reflected here is the one that goes in this direction, goes from node 1 to node 2 or from node 2 to node 5. And that's reflected in the total distance, 7, and in this record that we maintain here, that the optimal distance that takes us to node 5 goes to node 2 in the prior iteration. And now we examine our set of distances and we can see that we know we will grow in the next iteration our set of knowledge from nodes 1 and 2 to nodes 1, 2, and 3, because that is the node that has the shortest distance now to the origin. And indeed, our set of ignorance is now reduced to nodes 4, 5, and 6, and the nodes of knowledge is increased, is augmented to nodes 1, 2, and 3. What this means is that we have the optimal path to go from node 1 to nodes 1, 2, and 3. And we don't yet know the optimal path that goes from node 1 to nodes 4, 5, and 6. In the next iteration, we now look at the optimal distances we have obtained, which includes the nodes which are in our ignorance set. And we see that the ones that have the shortest distance is nodes 4 or 5, both equal. We could pick one or the other. As you can imagine, there's no particular order in the way these nodes are ordered in our system. The significance of node 1, 2, 3, 4, 5 has no particular ordering notions to them. For simplicity, we will pick node 4 as the next one that we're going to be performing our analysis. And now, because of that, we augment our set of knowledge to include node 4, and we decrease our set of ignorance, removing node 4. Node 4 has its own collection of next door neighbors, which now includes node 6. Therefore, we are able to bring node 6 into our analysis, finding its temporary optimal shortest distance and its previous node we went through to get to node 6 as reflected in our memory list. We now perform our comparison analysis and we see that the next node we can grow with is node 5, represented by this distance 7. Therefore, we are able to continue our iteration into iteration number 5, which contains us the single ignorance set given by node 6 and our knowledge list given by nodes 1, 2, 3, 4, and now 5, reflected by the distances that we have here. Now we examine the neighbors of 5, which includes node 6, and we can see that the distance 1 allows us to find a better shortest distance to node 6 by going through node 5, increasing the distance from node 5 by 1, which is 8. The result of this algorithm is that we have now obtained the shortest distance from the origin, Toronto, to each of the nodes in our map, and we have the memory of the previous city we have to go through to get to our city. Therefore, the optimal path to go anywhere from Toronto to either node 6, node 4, or node 3 can be read off from the sequence of memory lists that we have obtained, that we have maintained, listed by L, and we know in advance the distance that we will have to travel to get from node 1 to any of the nodes in our map. But now the question arises how long it takes to do this. In practical applications, we'll have millions of nodes in our graph. If one tries the brute force approach and just tries all the possible combinations, that's millions factorial. That number is just huge, untenable. You can't work with it. The advantage of the Dijkstra algorithm is that you can actually do it. The complexity of it is n squared, where n is the number of nodes. So it's something that if we're dealing with millions, this is 10 to the power 12, which is something that we can actually do in modern day computers. There are improvements that achieve a complexity which is much smaller, like n log n, for example, logarithm of n multiplied by n. That makes it a lot faster, and the actual modern day applications of this use heuristics and other elements of artificial intelligence, machine learning, that makes these algorithms even faster. So it won't take us longer to solve the problem than to actually get to New York.